If we have a continuous flow of fluid in a pipe, which means no air bubbles or anything, or no water bubbles if it's air, the fluid could be air, the same amount of water must go through one cross-sectional area per time as another cross-sectional area per unit of time. And since at a very wide point of a pipe where there's a large cross-sectional area, there's a lot of fluid that can go through even if it's going slow. So once the tube contracts down to a narrower cross-sectional area, the fluid has to increase its speed to get the same amount through per time as over here where it's wider. So you generally get a faster flow where it's narrower. But in this example with the arteries and the capillaries, it's kind of a little bit confusing, because in the narrower capillaries the blood is flowing slower. But that's because there's just so many capillaries that overall the cross-sectional area of the capillaries is bigger when you add up all the, I don't know how many, I guess we'll figure it out, probably thousands of capillaries that are in the body compared to just one aorta. Even though the aorta is a lot wider than the capillaries, the overall cross-sectional area of the capillaries is wider than the aorta. So here's our aorta, here's thousands of small capillaries, and we need to find out how many capillaries there are. But we already know the speed of the blood in the aorta and the capillaries. 40 centimeters per second in the aorta, 5 times 10 to the 4th meters per second in the capillaries. And we have to make these units consistent. We have centimeters per second and meters per second. And since everything else is given in centimeters, it'll be easier to go do one conversion from meters to second to centimeters to second, rather than a bunch of centimeters a second to meters to second conversions. So let's put this into centimeters per second. There's our conversion factor, and we just take that exponent, shift it 2 places from -4 to -2, or we could pretty easily write that as just 0.05 centimeters per second. And let's just call this VA for your aorta, VC for capillary. So this equation we saw a minute ago in the slides, it deals with velocity and area. So we could easily figure out the area, the cross-sectional area of the aorta, because we have its radius. We know that the cross-sectional area is 2 pi times the radius squared. And remember, we're just going to go ahead and use centimeters for everything. So we can actually just put in centimeters here. And keep in mind that we can only use this 2 pi r squared equation because the aorta is circular. So we're finding the area of the circle, which is the cross-sectional area. It wouldn't work if you had square arteries. But anyway, we get 9.05 centimeters squared as the area of the aorta. And as our variable, let's call that A aorta. Now let's think back to that equation I was talking about. V1A1 equals V2A2, which in this case is the velocity of in the aorta times the cross-sectional area of the aorta, and then that's equal to the velocity in the capillaries times the total area of all the capillaries. And that's what we can find with this equation, the total area of all the capillaries put together. And once we find that, we already know the radius of one capillary, so we know the cross-sectional area of one capillary, so we can just figure out how many of those we need to get this total cross-sectional area. So once we solve for that variable, we get that, and let's put in some numbers. Oops, I put in A when I should have put in V. We'll get rid of that A and put in V, and everything's better. And now we have our numbers in there. And that's a lot of cross-sectional area for all your capillaries to have. So a very small cross-sectional area for one capillary. But we know that if we multiply that by the total number of capillaries, which we'll call x, we have to get the total area of all the capillaries, which we saw a second ago, which is over 7,000 centimeters squared. So let's solve for x. And here's our answer, 2.88 times 10 to the, dramatic drum roll please, 10 to the 10th power. That's over 20 billion capillaries. Google tells me there's at least 10 billion. So we're in the right ballpark here.